Alright, so today we're going to have a short lesson answering basically 3 questions, okay? First of all, how do we deal with it when we've got multiple logarithms that have the same expression, okay? Really it should be the same base. We can condense those down into just one logarithm, okay? How do we deal with the logarithm of an expression where you have multiple things inside one log? You can expand it so that it's a bunch of different logs. And then thirdly, how do we evaluate logarithms that our calculators can't do? Okay, our calculators have built into them a log base 10, our common log, and the natural log, which is the log base e. Okay, but not all of our calculators can do logs of other bases, okay?
I know how to do that.
So now, if your calculator can, the reality is, the way that we do this is so simple, it's so simple, it's faster to do it that way using our change of base formula that we'll look at, than it is to go into whatever menu you have to get the logarithm, you know? So, but anyways, we'll look at that here in a sec. Alright, so let's look at some of our laws. Okay? First of all, we have the product property and the quotient property.
That's where you bring the exponent out front, right?
Well, that's our another law that we're looking at here.
Power property.
Yes. Here we have the product and the quotient. I want you to just tie this together. We're not going to go super in detail on all these examples, but I want you to think. Logarithms are what? Exponents, okay? What do you do with the exponents when you multiply stuff together?
Add the exponents.
You add the exponents, right? That's where this rule comes from. What do you do when you're dividing things? You subtract the exponents.
Looks like the same properties as exponents.
Exactly. That's where each of these properties comes from. Okay? So that's why if we have the log of things multiplied, we can split it into 2 separate logs being added together. We're adding the exponents. If we have 2 exponents, or 3 even, added together, we can put all those together as a multiplication problem inside one log. So here we have expansion, here we have condensing. Okay? Yes?
What's that little dot over the plus? Is it not supposed to be?
Oh, that's just a glitch. That should be addition still.
Okay.
That was just a glitch when I exported the file. There we go. There. Alright, so just to see how this is useful, if you look at the equation to the right, we can't solve that equation as it is, alright? So what we have to do is we have to use this property to rewrite this as the log base 2 of 3 times x equal to 8. Okay? Now the log base 2 of 3x equals 8, we can now rewrite as an exponential. Okay, how would I rewrite this?
2 to the 8 equals 3x.
Very good. 2 to the 8th equals 3x. And 2 to the 8th is 256. That's 3x, so we divide, and we get 83 1/3. No, 85 1/3.
Did you do that in your head, or did you just you've done that so many times that you knew it?
Well, I know 2 to the 8th is 256 because of computers. 8 bits in a byte.
Right.
And so in binary you have 0 or 1. The biggest number you can make with 8 bits is 255 because you start at 0. So there's 256 numbers. That's why if you look at an IP address, you know what IP addresses are?
Yeah.
The highest number an IP address can hold is 255. In IPv4, yeah. IPv6 is different. But that's okay. Techie stuff. But yeah, there's the relationship there is, you know, the 256. There are only 256 different numbers that you can hold in an 8-bit character. So, but anyways, we got our answer. The key though is using that logarithm rule, the product property, to get it down into one logarithm, okay? Similar thing here on this equation at the bottom. We have the log base 3 of x minus the log base 3 of 5. So how would we rewrite that?
Log base 3 of x divided by 5, or, yeah, x divided by 5.
Yeah, the log base 3 of x over 5 equals 2. So now I can rewrite the whole equation as an exponential equation,
So
which,
3 to the second equals x over 5.
yeah, good. 3 squared is x over 5. So you multiply and x is 9 times 5, which is 45. Okay? So the goal here on these is to get it down to one logarithm so that we can rewrite the equation as an exponential. Okay? We will expand it sometimes in order to simplify things a little bit easier. Okay? But the condensing process here using these rules is particularly helpful in solving equations. All right, so we talked about those two properties. Here's one other property. This is the one that Kate mentioned earlier. Okay, and this is when you have a power. All right, we have the log of m to the k power. Now remember, we're talking about exponents. What did you get when you were raising a power to a power? What did you do with your exponents? You multiplied them. So guess what? You're going to multiply the power k by the power that you get with the log. Okay? It's the same concept that's behind x squared cubed is x to the 2 times 3, x to the 6th. Okay? Same concept is at play right here, where we're dealing with an exponent inside a logarithm. You can pull it out as a coefficient, or like you can see down here, if you have a coefficient, 4 times the log of 2, we could rewrite that with the 4 as the exponent of 2. So it's the log of 2 to the 4th, or the log of 16. Okay? In various situations, it's going to be helpful sometimes to pull the exponent out. Sometimes it's going to be helpful to pull that coefficient in as the exponent. All right? Here's a case where pulling the exponent out might be helpful. All right? Initially here, we only have one logarithm in this equation, so you could rewrite this as an exponential. 4 to the 16th power equals x to the 4th. But 4 to the 16th is a really huge number. Okay? You can make your life a whole lot easier if you first of all pull that 4 out in front, so now it's 4 times the log base 4 of x equals 16. And now, since it's 4 times the log, I can divide both sides by 4. So now it's just the log base 4 of x equals 4. So what does x equal?
16.
4 to the 4th, okay? Which again is 256. Okay. Does that make sense?
Yep.
Okay. So these are laws that you've used a little bit in the past. We want to use them more, apply them more this year. But there's one other thing that we look at, and that is change of base, okay? Before we get to that, let's practice a couple of these here. Expanding. All right. So on part A, all right, we'll do one together and one on your own here. Part A, we have the log base 4 of 5x cubed y. So how would I expand that out? Okay.
Log base 4 of 5 plus log base 4 of x cubed plus log base 4 plus of y.
Okay, good. We see multiplication happening twice here. So we can expand that out so that it's 3 separate logs added together, okay? Anything else we can do?
Yeah, the second term, can't that be 3 log base 4 of x?
Perfect, good. And now we've fully expanded this, okay? We have the log base 4 of 5 plus 3 times the log base 4 of x plus the log base 4 of y, okay? So when we say expand, what we're talking about is there should not be anything multiplied or divided inside the logarithm, okay? And also there should not be an exponent left in the logarithm, okay? Now, there may be things added or subtracted inside the logarithm. There's no way to pull those apart, okay? But we shouldn't still have like a 5y inside of our logarithm, okay? All right, so take a minute here and work out b on your own. We'll see what you get. All right, so after we identify the square root as the 1/2 power, what did you guys do?
Bring the 1/2 out front.
Okay, so what does this look like here?
1/2 natural log times the quantity 3x minus 5, or of the quantity 3x minus 5, minus natural log 7.
All right, what do you guys think about that?
I don't think you'd be able to like go any further, would you? I don't know.
You just do 1/2 natural log 3, 1/2 natural log.
Okay, I thought since there's subtraction in there that you can't. I don't know.
Yeah, because that's correct. Because there's subtraction in there, we can't really do anything with that exponent. It's kind of like, it's kind of like when you have a binomial raised to a power, you can't just multiply the first ones and multiply the second ones.
Right.
You've got a FOIL, all right? So same way in this, we can't like split this up into multiple logs. I mean, I guess the only way you could is if you factored out a 3 from the 3x minus 5, but since it doesn't come out evenly, it doesn't really make sense to do that. All right, so that would be fully expanded. We have the exponent out in front as a coefficient, and there's something added and subtracted in this case inside, so we can't expand that out. We do have the minus ln of 7 because we were dividing by 7. Okay? That make sense?
Makes sense.
All right. All right, let's try a couple where we are condensing these. Okay? Let's condense A first of all. All right, we have 1/2 log base 10. Why do they put a log base 10? I don't know. Because we can just put log, right? So how would we first of all simplify 1/2 log base 10 of x?
Log of x to the 1/2, or x squared.
No, you're right the
X to the
first time.
1/2, x to the 1/2.
Log of x to the 1/2, which is square root of x. Okay, so log of root x plus, how would we simplify the 3 log of x plus 1?
Plus x plus 1
Yeah.
There you go, log of x plus 1 to the third. We're taking that coefficient and we are putting it as the exponent. Just like we took the coefficient 1/2 and we made it our exponent. Okay? Now, what's our final result here?
Log base 10 root x times x plus 1 cubed.
Yeah. The whole thing here would be inside our logarithm.
They're both the base 10, so you can combine them.
Exactly. They're both the same base, so we can combine them. And that is necessary, okay? We didn't make a huge deal of that because, I'm not trying to be tricky with you, okay? But just understand, if you do have different bases, you cannot use these rules, okay? We're not going to do all 3, but let's go ahead and try C. Okay. What do you propose that we do first?
That 1/3.
Cube root of it.
Put the whole thing to the root 3.
Cube root
So wouldn't that be
Okay.
log base 2 cubed root of x times log base 2 cubed root of x minus 4?
So log base 2 of the cube root of x plus the log base 2, forgot my 2 here, of the cube root of x minus 4. You guys agree with that?
Yeah, I agree.
Okay, good. Yeah, if you distribute this 1/3 into each of these as a coefficient, then you can pull the coefficient in as an exponent. Okay, and the 1/3 power is the same thing as the cube root. Okay, so good, that looks good. Where do we go from there?
Combine them.
How are we combining these?
Log base 2 of the cube root of x times the cube root of x minus 4.
Good. And by the way, since they're both cube roots, we can multiply those together and just make it the cube root of x times x minus 4.
Can we just
Distribute out the
Okay.
x.
You could distribute the x if you want, make it x squared minus 4x.
take points off of you
No. Okay? Now, by the way, there's variety in how you could have approached this one. Some might say, hey, I'm going to leave the 1/3 till last, and I'm going to make inside the brackets the log base 2 of x times x minus 4. Okay? Then they multiply by the 1/3. Okay? But it really doesn't matter. Whichever way you prefer, whichever order you prefer, as long as you're careful, you can do it. Okay? Alright, so we've answered our first two questions. The last question I want to answer here is, how do we deal with bases that are not something our calculator can do? Alright, and this is where we have the change of base formula. I want to start with an example. Let's say I have b to the x equals a. Alright, how would I solve this equation for x?
Take the log of both sides.
Okay, we could take the log of both sides. Okay, so I have the log of b to the x equals the log of a, right? Now what could I do?
You can move the x to the front and divide by log b on both sides.
Okay, I could pull that x out to the front. X times the log of b equals the log of a. And then you're right, we can divide both sides. So it's the log of a divided by the log of b. Okay. And now I know what x is. Alright. Now, Katie chose to use what as the base of her log?
10.
10. Could I have used the natural log?
Sure.
Could I have used a log base 3 if I wanted?
Yeah.
Yeah.
Yeah. The fact of the matter is, we can use any base we want as long as we are doing the same base on both sides. Okay? What this allows us to do, if you think about this, an alternative way of solving this equation would have been to do this. I could have taken the log base b of b to the x, and that would have been the inverse operation. And in fact, that's a way that I think it'll be helpful if you get used to solving them this way. Alright? But if I do that, I have to take the log base b of a as well. Alright? Well, the fact of the matter is, we don't necessarily know how to do a log base b. What if b is like 3? Or what if b is a 1.06? Alright? That's where this comes into play. Now, since I had a base of b, but my calculator can't do a log base b, I can change that logarithm base to whatever I want as long as I put the argument in the numerator and the log base c of my original base in the denominator. Okay? The base goes on the bottom. Alright? So that's where we get this change of base formula. Alright? I always like deriving that because a lot of times people will solve the equation the same way that you guys did right here. When you're doing that, you're really just re-deriving our change of base formula over and over and over and over again. So you're doing the same kind of work lots of times. Okay? Yes?
Why did it go from the log base b of b to the x and the log base b of a to x is equal to log base c of a over log base c of b?
Well, the idea is this. The idea is b might not be 10 or e. It might not be something that our calculator can actually do for us. So we got to figure out a different way. And sometimes it's not even a calculator thing. We'll see down here, there's actually a time when it'll let you solve a problem in your head that otherwise you couldn't. Okay? Let's actually look through these couple examples here, and I think you'll see why here.
Did the base change from b to c, or is that the
Yes.
same number?
No, it changed from b to c. So like it was a log base 3 of 7, so we changed it to a log base 10 so that we could actually punch that into our calculator. Or maybe we changed it into a log base e so we could use the natural log on our calculator. Okay? Now, if I'm asked to find what the log base 2 of 9 is, there's no common factors here. There's no real good way of doing this other than using our change of base formula. I'm going to take the log of 9 over the log of that original base 2. Okay? And you're just punching it into the calculator at that point.
They must round
Alright,
off.
so we get here 3.17. Yeah, for E, they just did a table. If you do a table, basically, you can keep going and going, making x bigger and bigger and bigger with that 1 plus 1 over x to the x power. E is the limit as x approaches infinity. A little bit of calculus there for you. Okay, that's the definition of what E is.
So how come that's
But it's-
natural?
Well,
Yeah, like how
it's
they-
built off of, remember our growth formula is 1 plus the rate of growth to the t power.
Okay.
Okay?
Makes sense.
Whenever we were compounding more than one time a year, because our rate was usually given in a year, we would divide the rate by the number of times it compounded, and then we would convert our time to compounding periods instead of just years. All right? Well, if you think about this, as k gets huge, all right, that r really becomes irrelevant what it equals, so you could just use a 1. All right? And also, you know, this is going to get huge as well. So that's where it has a similar structure to this. Okay, so,
See, yeah.
and if we wanted to compound continuously, or if we want something that's growing continuously, you know, k is going to be getting huge, because it's not just compounding 12 times a year, or 4 times a year, or even daily 365 times a year. We want it to compound every moment, which is like immeasurably small. So that's why it's going to infinity. Okay? So that's where that's derived. Okay. But you can use, here's the thing, on your calculator you can use log of 9 and log of 2, or you could hit the natural log of 9 over the natural log of 2, and it'll work as well. You'll still get 3.17. Okay?
It's just easier just to log though.
Yeah.
If it's second and log.
Okay. Now here, we also see we could do the log of 16 over the log of 8 on the calculator, and you'll get 4/3. But here's a case where not just jumping immediately to the calculator can come in handy.
So you could just do log of 2.
Yeah, notice that our base 8 is 2 to a power, but also 16, the argument is 2 to a power. If you recognize a case where both your base and your argument are a power of the same number, you can change your base to be that number. And 2 to the 4th power is 16, 2 to the 3rd power is 8. So if I change my base to 2, I can figure out that it's 4/3.
So we couldn't just do the log of 2 and it be 4/3?
You'd have to do the log base 2 of 16 divided by log base 2 of 8. But the whole point here is that you wouldn't want to do this on your calculator. The reason you would change it to 2 is because you recognize, hey, I can do this in my head. Okay? So same thing, like if I had, let's say I had the log base 27 of 81. Okay? 27 and 81 are both powers of 3. Okay? So maybe even as I'm writing it, I could say I'm going to make that the log base 3 of 3 to the 4th over the log base 3 of 3 cubed. Because 81 is 3 to the 4th and 27 is 3 cubed. So this would be 4/3. Okay? So that's one way we can use the change of base formula to very easily evaluate some of these without even using the calculator. Okay? Now, you might say, okay, where will this come into play? Let's look at one example and then we'll be done here. Okay? When we were looking at growth problems earlier this week, we were solving for things like, after 5 years, how much will there be? Okay? But often that, isn't necessarily as useful as, hey, we've got a goal here. When are we going to reach that goal if we continue to grow at this rate? Okay? For example, here we have a school district. Right now, they know that they've been growing at about 3% every year as far as how many students they have. Okay? Right now we have 10,000 students. However, our facilities can currently only hold and accommodate 15,000 students. So how much longer can we go before we're going to have to start building more buildings and all of that? Okay? Well, this is where our growth formula comes into play. The amount at a given time would equal what? How would we set this model up in this case?
Well, this continuing, right?
Well, look at our rate. Our rate is 3% annually, right?
It's yearly.
Yeah, we're going to basically, the number of students you have in a given year may fluctuate a little bit, but that 3% is going to be like compounding every year.
Alright. So A1 is 10,000.
Okay, good. Your starting amount times what?
The rate. Wait.
1 plus
1 plus the rate, so it's 1
the rate over.
Okay,
T.
1 plus 3%, right? So 1 plus 0.03, 1.03. So every year we're going to have 3% more than what we started. So it's 103% of what we started with, right? And then that's going to be to the t power. Okay? This is why you got to be able to construct these models here using that growth formula we looked at Monday. All right? Now, we can accommodate up to 15,000 students. So what are we going to do with this?
Less than or
Oh, yeah.
equal to 15,000.
Okay, yeah, we could make it less than or equal to 15,000. Okay? So now we can solve. We're going to divide by 10,000, and we get 3 halves equals 1.03 to the t power. And it doesn't matter if you treated this as an equation or as an inequality, okay? But now what do we do? How would we solve this exponential equation?
Take log of both sides.
Take the log with what base?
Natural 10.
That's possible. Let's do it so that we can just use that change of base formula rather than rederiving it every time. The log with a base of... What's the base of our exponential? 1.03. So what's the inverse operation of an exponential with a base of 1.03?
A log of the base of 1.03.
Yeah, a log with a base of 1.03. Okay? So, those are inverses, so now I know the time is less than or equal to the log base 1.03 of 3/2. So this is where the change of base formula comes in. We have the log of 3/2 divided by the log of 1.03. That we can punch into our calculators. So we get t is less than or equal to 13.7. Okay? So theoretically, somewhere in that 14th year, we're going to reach capacity. Okay? So,
Facilities.
yeah, we need new facilities. So if it's going to take us, 5 or 6 years to do all the blueprints, the planning, the fundraising, all of that kind of stuff to be able to build this thing, we need to get going on this project in the next, 6 or 7 years in order to not reach capacity. And really, we'd like to have it done probably a little earlier than that, just so we're not really packed out. Okay?
I don't know, like real life, the rate could get, faster, so.
Exactly, yeah. So but guys, this is what, not just a school district, but think about like a big city. Looking at the volume of traffic on their roads. Right now our roads are running at this much capacity without being total gridlock. Or right now, our subway system or our medical facilities can only handle this many people. If our population continues to grow, when are we going to meet capacity? So we need to plan ahead. This is kind of stuff that like a civil engineer might have to think of, or a city planner might have to think ahead on. We need to make sure our facilities keep up with our population growth. Businesses too. Your factory can only produce a certain number of units a day. So if your business is growing and you're reaching that, you got to figure out when you're going to reach capacity for production, and you need to either raise your prices to lower the demand a little bit, or you need to get better production to be able to meet the demand. Okay? So a lot of cool stuff that we can do solving applications like this. Okay? All right.